Almost every slanted cut through a donut gives you a wobbly, pinched curve, an oval, a peanut, a figure 8. But there is one exact slant where the same cut folds open into two flawless circles instead. Not near circles, circles. You already know two circles hiding in a donut. Run your finger around the outside the long way, that is one. Follow it around the tube, through the hole and back, that is another. Two obvious circles. One note before we cut. This is a perfect mathematical donut, a rigid surface, no soft dough, no glaze, just a tube bent into a ring. Mathematicians call it a torus. I will keep saying donut. So here is the question worth your time. Is there a circle sitting on this donut that is not one of those two? A hidden one. To find out, we start cutting. Push a flat plane through the donut and look at the curve where they meet. That curve is the cut. Tilt the plane differently and the curve changes shape. Lay it flat, straight across the middle, and you get circles, but only the boring ones you already knew. Two rings, one inside the other. Nothing new. Now tilt the plane. The cut stops being a circle. It bulges to one side, pinches in, becomes that peanut. Tilt further and it pulls itself into a figure 8, which is exactly what you would expect. A donut is a curved, bulging thing. Push a flat sheet through it on a slant, and of course a lumpy curve comes back. Except at one precise tilt. Hit that exact angle and the lumpy curve snaps cleanly into two perfect circles crossing each other. The whole question is why that single angle does what no other angle can. To see why, forget the surface for a moment. Look at the circle running down the very middle of the tube. Call it the spine of the dough. Its radius is the big radius, from the center of the hole out to the center of the tube. The cutting plane passes through the dead center of the donut, tilted. So as you travel along the spine, you climb above the plane, then drop below it, then back. The spine swings away from the plane and returns, twice around the loop. Here is the exact tilt. Set the slant so its angle has a sign equal to the tube radius divided by the big radius. That one condition is the entire trick. With the slant set right there, the farthest the spine ever swings from the plane is exactly one tube radius. Not roughly. Exactly, at the 2 points where the spine rides highest and lowest. Now remember, the dough only reaches out from the spine by one tube radius. So at those two farthest points, the surface of the donut just barely touches the plane. 2 kisses, and nowhere does it push past. Everywhere else, the spine is nearer than a full tube radius, so the plane cuts straight through the dough, touching at 2 points, slicing through in between. That is what makes this cut different. It is pinched to a single point at each of the 2 kisses, a curve that touches itself twice. And a curve that pinches to 2 points is really 2 separate loops, crossing at those points. There they are. The claim now is that each loop is a perfect circle, which should bother you. The donut bulges and curves, a slanted slice through it ought to give a stretched oval, not a true circle. It smells like a trick. It is not, here is the reason. Take one loop and find its center. It is not the center of the donut. It sits off to the side, shifted by exactly one tube radius toward the fold line of the cut. Each loop has its own center, one on each side. Follow a single point as it travels around that loop, measured from its offset center. It moves in 2 perpendicular directions at once, along the fold line and across it. Its reach along the fold line is the big radius times the cosine of how far around it has gone. Its reach across is the big radius times the sine, the 2 perpendicular sides of one right triangle. And the distance from the center is that triangle's long side. Cosine squared plus sine squared is always 1. So that distance never budges. It stays pinned at exactly the big radius the whole way around. A point that holds the same distance from a fixed center all the way around is the definition of a circle. So the loop is a circle, and its radius is the big radius, exactly. Pick any other tilt, and that clean split falls apart. The two sides stop squaring up to the big radius, the distance starts wobbling, and the loop sags back into an oval. This one angle is the only one where the numbers close. Put real numbers on it. Big radius 3, tube radius 1. Measure the loop and its radius comes back 3.000 everywhere you check, with the two centers sitting exactly 1 unit on either side of the middle. These are called Villarceau circles, after Yvon Villarceau, a French astronomer who wrote them down in 1848. Plenty of people who have handled donuts their whole lives have never met them. So count the circles you can lay on a donut. Around the outside, the long way. Around the tube, and this new diagonal pair that cross each other, 3 kinds in all. Which sets up one final question. Pick any single point on the surface of the donut. Any point at all. How many of these circles pass through that one spot? The answer is 4. Through every single point on a donut run exactly 4 circles, all lying flat on its surface. There is the horizontal one, going around the big way through your point. There is the tube one, wrapping through the hole and back through the same point. And through that 1 point run both Villarceau circles, the 2 diagonal ones, crossing each other right there. 1 point, 4 circles threaded through it at once. That is the hidden weave of a donut. Every point on it is a knot where 4 circles meet. 2 you could have guessed, and 2 you would never have found without tilting the knife to exactly the right angle.